Hello children and welcome everybody to the class of science. We are learning magnetic effect of electric current, chapter number 13. And in the previous video lesson, we learned about the working of electric motor, which works on the principle that when a current carrying conductor is placed in a magnetic field, it experiences a force. We're going to move ahead with the chapter, and today's topic is electromagnetic induction. So far we have learned that the only way to produce electricity is with the help of cell or a battery. But this is all right, and this is very convenient when we are using the batteries in the toys or in the clocks or even in your mobiles. But imagine you have to supply electricity to the whole town. You have to supply electricity around the world to the millions of houses. Are you going to build up the batteries? Imagine the amount of chemicals we are using. Imagine the mess. So the question arises is, can we generate electricity without batteries? Is it possible to generate electric current without batteries? So I guess the big question which now we're going to explore is, can we generate electricity without using batteries, without using chemicals? Let's see. We have learned that when we connect a battery or a cell to the coil of conducting wire, it produces magnetic field around it. So electric current can generate magnetic field. This is what we have learned. But a curious scientist, Michael Faraday, he thought the other way. He thought, can magnetic field generate electricity? Is it possible that we generate the electricity with the help of magnetic field without using batteries, without using chemicals? And to prove this, Michael Faraday did many experiments. So children, let's imagine that now we are Michael Faraday and we will just try out certain experiments to find out, is it possible to generate electricity with the help of magnetic field? Come on, let's do it. So how do we do that? We will need a conductor for that. So we have taken a ring and we will need a current sensing device. And galvanometer is a current sensing device, or you can say it's a device which is used to detect the presence of current in the circuit, and it is also used to find the direction in which the current is flowing in the circuit. But for our experiment, to make it more interesting, in place of galvanometer, let's have the electric bulb. So if the current is generated in this coil, the bulb will glow. And how we are going to generate electricity? We are going to generate electricity with the help of a magnet. So I'll keep the magnet near to it. And the bulb should glow because we are generating electricity with the help of magnet, but it's not happening. So our experiment is not proving that the magnetic field can generate electricity. This magnet is producing magnetic field around it, but since there is no glow of bulb, does that mean that our experiment is not working? Does that mean that magnetic field doesn't produce electric current? So what do we do then? Let's pack up and go home. Is that so? Okay, I'll move the magnet behind. Can you see the flash there? Oh, let me take the magnet near to the ring. Oh, again, can you observe anything there, children? Whenever I am moving the magnet backward and again bringing it forward, could you observe that flash? So something is happening. I think our experiment is going correct. Every time I am taking the magnet backward and bringing it forward, there is a flash seen there in the bulb. Can you observe that? So we are moving the magnet backward and front, and we can observe that the bulb which is attached to the conducting wire is flashing. That means our experiment is working. Let's go other way. Let's move the coil towards the magnet. Let's do that and observe. Can we see the flash again? Oh yes, when you are moving the coil towards the magnet and taking the coil backward, then also you can see the flash. So either we are moving the magnet or we are moving the conductor. In both the cases, we can see the flash of the light there. What does that mean? So whenever I am taking this magnet towards the conductor, I am actually changing the magnetic field. I am disturbing the magnetic field, and during that time there is a flash in the light. At the same time, when I bring this conductor towards the magnet already has its magnetic field around it, and when I bring this conductor towards the magnet, again I am disturbing the magnetic field. Again the magnetic field is changing, and during that time again we can see the flash. This shows that the current is induced into the conductor when there is change in the magnetic field, and this is what is called as electromagnetic induction, children. So I can define it like this: the process by which a changing magnetic field in the conductor induces a current in another conductor is called electromagnetic induction. Alright, so the process by which changing magnetic field induces current into the conductor is called as electromagnetic induction. We have also observed one thing here, and that thing is the relative motion between the current carrying conductor and the wire is not mandatory. Meaning is that it's not necessary that the wire and the magnet should move at the same time. It can be either the magnet moving or the conductor moving, and in both the cases we can see that flash of light. That means change in the magnetic field induces current into the conductor, and that is electromagnetic induction. Alright, let's observe this now. We have a coil of a wire, and near to that we have placed a magnet. The magnet is stationary, it is not moving. You can observe that when the magnet is not moving, the galvanometer, which is connected to the two free ends of the coil, is stationary. It is showing 0 reading. That means there is no current into the coil. So when there is no change in magnetic field, when the magnetic field is intact, it is not disturbed, no current is induced into the coil. That is the reason the galvanometer pointer is at 0. But the moment you start moving this magnet in and out of the coil, you can see the deflection in the galvanometer. Can you observe that? This shows that when you change the magnetic field around the magnet, electric current is induced into the conductor. So I can say like this: moving magnet towards a coil induces a current in the coil whose direction and magnitude is given by the galvanometer. Meaning is that when the direction of the magnet is reversed, see, once we are taking the magnet inside, that's one direction. Once you are taking it outside, that's the other direction. So when you are changing the direction of the magnet, you can see that the deflection in the galvanometer also changes. Once it is going right, then it is coming to left. So when the direction of magnet is reversed, the current also reverses, and this is indicated from the galvanometer. Now observe one more case. Look at this. I want all of you to count the number of turns of the coil. In the first case it is more, in the second case it is less. And now just check out the deflection in the galvanometer. You will observe that in the second case the deflection is not much, it is less. What do we infer from this? We say that the induced current is directly proportional to the number of turns of the coil of the wire. Greater the number of turns, greater is the current produced. So when the number of turns are less, the current produced is also less, and that is the reason the galvanometer is showing very less deflection as compared in the first case. In the first case, if you observe, it's a full deflection there. whereas in the second case it is hardly anything. So number of turns is directly proportional to the current produced in the conductor. Alright, so this is one method of producing the electric current by changing the magnetic field around the magnet. Let's understand the second method. This experiment was done by Faraday, and he is also called as the experimental scientist. Alright children, so what is the second experiment? We have taken the coils, two coils we have taken of copper. To the one set of coil we will attach a plug key and a battery, and we will complete the circuit. The second coil is not attached to the first coil, but it is just placed near to the first coil. First coil is a current carrying coil because we have attached a battery there. To the second coil we will just attach a galvanometer. Check out children, to the second coil we have not attached a battery. It is just a galvanometer attached to the second coil, and to the first coil we have attached a battery and a tap key. So the moment you tap the key, you will observe that the galvanometer pointer has changed. Please check out there. Now I'll take out the key. You can also see now the deflection is there, but in the other direction. So every time I am tapping the key, and during that time you will observe that there is a change in the deflection in the galvanometer, because when I close the circuit of the first coil, current started flowing through that and it produces magnetic field around it. The moment I take the tap key up, that means the magnetic field is disturbed. Again I will tap the key, again the magnetic field is produced. So every time I am tapping the key, taking it up, again tapping it, I am changing the magnetic field, and that change in magnetic field induces the current into the coil which is placed adjacent to the current carrying coil. Alright, so this way also current can be generated into the conductor. So we can say that current is induced in a coil when a current carrying conductor is brought in its vicinity. Vicinity means what? When it is brought near to the current carrying conductor. Have a look at this children. See, the magnetic field is produced around a coil when you pass electric current through it. The adjacent coil is not attached to the battery, but then also you can see that the bulb is glowing because this tap key is continuously pressed down, up, and due to that there is change in magnetic field, and that change in magnetic field is glowing the bulb. That means electric current is induced into the coil which is placed adjacent to the current carrying conductor. So the current is induced in the secondary coil due to change in the magnetic field of the primary. Since we have made use of two coils here, we will call the current carrying coil as a primary coil, and the coil which is placed just adjacent to this primary coil, we will call that as a secondary coil. Alright, so we have learned that there are two ways in which we can generate electric current, that is moving the conducting wire inside the fixed magnetic field. We have moved the loop of the conductor towards the magnet, that is the one way, and second, keeping the wire at one place and moving the magnet towards the wire. What is the meaning of induced current? The current which is produced by electromagnetic induction is induced current. Okay, so the type of current which is produced either by the movement of a magnet or by the movement of the conductor by changing the magnetic field is induced current. Now the question is, in which direction the current is induced in the conductor? That is given by Fleming's right hand rule. Do not get confused children, we have learned Fleming's left hand rule, which is used to find the direction of the force experienced by the conductor, and Fleming's right hand rule is used to find in which direction the current is induced into the conductor by changing the magnetic field. So what you have to do, stretch the thumb, forefinger and the middle finger of your right hand in such a manner that they are mutually perpendicular to each other. Look at the figure given there. If the thumb points in the direction of motion of the conductor, the forefinger in the direction of magnetic field, then the middle finger will always give you the direction of induced current. So this is how you can find out in which direction the current is induced into the conductor. Alright, so this is all about electromagnetic induction, and up till this we have the chapter, children. After this topic, the AC generator, DC generator, that topics are not there for this particular year. So here is, we can say that we have completed the chapter. In the next video lesson, we will revise some of the topics which are very, very important. But time being, I want all of you to go through this video once again and check out what is electromagnetic induction. So see you all in the next video lesson. Till then, bye and take care.